Oh, so today we're going to talk about teaching new tricks to an old micro by rating the datasheet. So this is what we're going to cover today, but we'll skip it so we don't spoil anything. So I'm Mark. I lead the engineering team at Marcus Engineering. We do offensive and defensive product security in highly regulated areas, medical devices, military, aerospace, that kind of thing.
And I am James. I'm our senior security engineer. I do some of the product design as well, but now I'm specializing more in embedded security, reverse engineering, code extraction, the kind of fun stuff we're going to talk about today.
All right, so the first thing we're going to talk about is how did we even get interested in this topic and this processor and the stuff that we're talking about today. So we actually started by doing some security research on a popular model of low-end electronic lock from a major brand. And of course, the first step to any evaluation is we got to get the firmware out. We got to see what's going on inside. So first move, buy product, open it up, start tearing it down. Got to figure out which of these chips is most interesting. Turns out this one right here, this is a microcontroller. And now the next step, what processor is it? What's the part number? What's going on? Luckily, they very helpfully wrote the part number right on the PCB for us. It was really convenient. So we did quick PCB reverse engineering. It was actually the easiest PCB reverse engineering I've ever done because they wrote all the part numbers right on the board for us. It was super convenient. I wish everybody was that thoughtful when they designed their PCBs. Oh, and so this part is a formerly NEC, now Renesys, UPD 78F9202. It's a 8-ish bit microcontroller. It's a little funky. It's about 40 years old at this point, but it's still shipping in products today, at least a few years ago. So now we got to figure out how do we get the firmware out of this thing?
So the first step in getting the firmware out of any chip like this is actually to go take a look at the manuals from the manufacturer and see, a lot of the times they'll document exactly how to use the programming port, and that's a great place to start. So in our case, thankfully, NEC did carefully document the flash protocol, what pins to use, how to get it into programming mode, commands to run, all the way up until, entire flowcharts of how to operate the flash programming mode, which is great. Not everyone goes into that much detail. And the pins that we physically need are broken out to a header as well, so it's very convenient to get physical access to the programming port. For the electrical communication and setup, we're going to just program a teensy to do that stuff and let us talk to it. So how are we going to use this interface to actually program it? To read it. We get it into programming mode, and we have to do some funny pulses and send the clock and then do some UART communication, and we go over to the list of commands, and we find the read command. There's not a read command. So that's a bit of a roadblock to getting the code out of this thing. What we would kind of normally do, what we've seen on other chips, and especially microcontrollers we've designed with, is that there is a read command, or there's a debugging interface that's going to let us upload a little stub that reads out the flash over some pin. And even if these are disabled by some security feature, they're great glitch targets. Willem and Greg yesterday had an exploit where they did that. Just glitch your way past whatever's disabling that. Not really possible on this because the facilities to do that are not disabled, they're non-existent. So we're going to have to take a closer look and read a little deeper into the programming manual to understand how we can use the commands that are there to get the data anyways. So part 2, attack of the datasheet. There's no read command. What else can we look for? We want to look at every command in detail and see if there's anything in there that interacts with the flash in an interesting way that's either going to intentionally tell us data about the state of the flash or potentially tell us information that maybe the designers didn't really think of about what's in the flash. So to start with, this is all the commands in the chip, and we're just going to go through them one by one. Even if some of these sound like they're probably not useful to us, we want to make sure we're not missing anything, any opportunity to get data out of this thing. So the first command we're going to look at is the programming command. It writes data to the flash. It changes ones to zeros. 0 to 1 is a separate erase operation. This would let us know what's in the flash by changing it. That's not really what we want to do initially. We need to find out what's in there first. So we don't really want to overwrite the data at this step, but we may come back to this. There's security set. This is interesting because it's described as a separate command, but it's clearly a special case of programming. It has the same command byte and just kind of refers to a bogus block number that's not documented. So that's kind of interesting. Maybe we can do something interesting with that block number, but we don't want to turn on more security, so this one doesn't immediately help us. Internal verify. So verify commands are usually a great target for this sort of thing, because if you can send the chip data and ask it, is this what's in the flash? You can learn something about that. And even if you have to send, 256 bytes where you could never possibly try all the permutations, it's a great candidate for side channel attacks. Can we see that, it takes longer or shorter or draws more or less power based on how much of the data was correct, and kind of fine tune that way. But the internal verify command in this chip actually does not take any data. It's not really clear exactly what it's doing, but it's either looking at the data that you sent along previously, or it's just doing some weird analog thing. Anyways, we can't send it data, so this isn't going to really help us. Block erase. I think the interesting thing about this one is that we could possibly knock out the security bits of this if it really is just another special block at a special address. But the security bits aren't what's preventing us from reading this chip. It's not disabled, it's just not there. So no block erase for now. Definitely don't want to do chip erase. I think that one's pretty clear. We'd like to have the data still there to read out. Block blank check. This would tell us if a block is erased. That does tell us something about the state of the flash. It could tell us something about the size of the program. If it's substantially smaller than the total size of the flash, that could constrain our search somewhat, but it doesn't really meaningfully tell us, what program is in there. Chip blank check. We really hope the chip's not blank. I don't think it is, because the product is working. And that really only leaves one command for us to look at, which is the checksum command. So this computes the checksum of one or more blocks. It starts at block 0 and then works its way up to whatever block you ask for, doing an entire block at a time and kind of chaining those checksums together. This is interesting because it has to read the flash to be able to do that, and that's a good thing because it tells us whatever part of the chip we're talking to right now, whether that's a boot ROM or some hardwired logic or whatever, it does physically have the capability to read flash. That is wired up somehow, and so that's a great start. This only works on blocks, but you can specify the start and end address, which is kind of funny. If it's only supposed to work on a block, that seems like you wouldn't really need to tell it that. So we'll see maybe if something interesting happens if we change those from what the datasheet tells us they're supposed to be. Basically, this is really interesting. We might be able to use this to get some information, enough information from the chip to know what's in it. So we can get the checksum of each block. That's a good start. Can we get the checksum of each byte? Can we just manipulate those offset and end addresses to ask for the checksum of each byte and just basically figure each one out? The only way for us to find out is to test it. So we're going to take this to the lab and run some commands and see, basically how it responds to the things that are defined in the datasheet and also the things that aren't. How to test this? We do need to do some special stuff. It's mostly a bidirectional UART communication, but it's not quite that simple. We can't just grab our favorite USB to UART adapter and plug it into a computer. We have to power it on and send a pulse on the clock pin and then 5 on the data pin and then release reset and send an 8 megahertz clock and do this all in, the right sequence for the right timing. So we're going to write a little Arduino program and run it on a Teensy just to bit bang everything and keep it really simple. And then we'll also throw the commands in there just to keep it all in one place. But in order to test these chips, first we have to find these chips. They're end of life now. Probably were not pretty recently, but they're gone from DigiKey and Mouser and those sorts now. Fortunately, they weren't too rare. Lots of sellers on eBay had some new old stock, so we were able to get some from China. It takes a little while, but ultimately not very hard to get a hold of these. We put it on a little breakout board and wired it up to a Teensy with a logic analyzer and everything just to make sure that, when we think we're sending the signals we saw in that picture, we actually are, and ready to send some commands. Very simple. Fortunately, this chip, there's no real framing or flow control. You send a command byte, you send some parameters, you get a status byte back, and maybe send some more data and status depending on the command. So just incredibly simple. If it's for some commands, you send extra. For the checksum command, we just send that number, B0, the block number, the offset, which is the start address, and the end address. And so we're going to run this exactly the way it appears in the datasheet, just to make sure that we have communications with the device, that it's working, that we're getting a checksum back for whatever's in there. And so we should send this and get the acknowledgement byte back and get a checksum. And we do. So that's great. We can start. We can start playing with this and changing it and seeing how it reacts. So first, to just mention, why do we want to change this? Why is taking a checksum of the whole block not good enough? That is because of the pigeonhole principle. So the checksum output is the function of the flash data input, and we want to turn that around and figure out the flash data input from looking at the checksum. But because there are many, many more inputs than there are outputs, we have about 16 bits of output and 256 bytes of input. It basically is not really possible. More than one input can result in any given output. So if we know the output, it doesn't really tell us what input is there. It rules out quite a few possible flash data combinations, but it doesn't meaningfully tell us what's in there. So we can get the 16 bits of output for a full 256 byte block, 2048 bits, but essentially we need the yellow bar to be taller than the orange bar. Otherwise, we're not going to know what's in the flash. If we had a single bytes checksum, we can just try every possible byte and see which one results in that checksum, because now we have less unknown data than we have information coming out of the checksum algorithm. And it's not always true, but in this case, having that 16-bit output uniquely identifies the 8-bit input, and that would let us find out exactly what that byte is. So it's time to try that. We're going to take the exact same command we sent before and change the end address from the end of the block 255 to 0. So we're asking for a checksum of block 0, start at 0, end at 0, exactly 1 byte. We're going to send this and see, do we get an ACK? Do we get a checksum back? Unfortunately, we don't. We get a not acknowledged byte back. This is a very vague kind of something didn't work value that doesn't give us any specifics about, well, I didn't like your end address, I didn't like the overall length, it just doesn't work. And we tried a few combinations, but the only one that we found actually worked consistently was actually doing the full block. So I guess that's what we're stuck with. We have to take a checksum of the whole block, but maybe we can still do something with that. Maybe we can learn some information about the flash data by looking at the power consumption of the chip while it's running that command. So we put a current shunt, just a little resistor, in the ground return path of the chip and looked at the voltage across that on an oscilloscope while we're running the checksum command to find out, can we see that if we know all the bytes are zeros or we know they're all ones, that we see more or less power being drawn, or it takes longer or not as long? And can we find more specific patterns than that? We can, a little bit. But unfortunately, we can only tell about 4 bits per byte, so we're doing slightly better, basically, than the Hamming weight of the input data. And that's a lot better than just having a 16-bit checksum, but it's still not quite good enough to actually find out what's in the flash. The yellow bar is still considerably shorter than the orange bar. So anyways, power analysis, that's advanced hard stuff, right? So we're just going to keep playing around with some commands from the datasheet and see what we can get them to do just in band. Conceptually, a single byte checksum works. If we could do it, we would be able to understand what that byte is. So if we can use the programming command to delete everything out of a block except for 1 byte, then that's the same thing, right? We have to do the whole block, but we know 2040 of the bits, and we only don't know 8. Conceptually the same. We could buy 256 of these things and delete a different byte out of each one. That would probably get expensive, so we'd rather do something a little bit better. So that would work. Let's go all the way to the end, delete the first 255 bytes, and then we only don't know the last one, and we can learn it from the checksum of that block. And if you can imagine just undeleting the byte before that, just getting it back, then we know the first 254 are 0, and we know the last one, and we can take the checksum, and we know that it is whatever value that is. And we can find that one. And we can work backwards and eventually get the block back. So obviously, undelete is not actually an operation on the flash, right? We can't do that, but we can do something conceptually similar that's still going to kind of let us work backwards through time. So if we imagine that we start with a 8-byte block and we don't know anything about the contents of the flash, It's totally empty, or it's totally unknown, and we also don't know anything about the checksums of that flash. The first thing we can do is the easiest thing, right? We can just take the checksum of that data. Then we can delete 1 byte and take the checksum again. And so now that's changed. We know that this is the checksum where just that 1 byte is 0. We can delete the next one and take the checksum again, recording these as we go and working our way up, storing these all until there's just only 1 byte not deleted. And at this point, it's like we said, there's enough information from the checksum to kind of flip this around and try every possible byte there to figure out what the real one is. It's that. We can go back to the previous checksum, and now we know the first 6 are zeros. We know the last one because we just figured it out. We can guess that one. And we can just work our way back through the whole memory until we've guessed every single byte in that block, and we know them all, and it matches our original checksum. And you just imagine doing this instead over 256 bytes and over 16 blocks, and we figure out the total contents of the flash. Basically, instead of learning the flash contents by figuring out what's already in there, we're knowing the flash contents by setting it ourselves. It's the same amount of information in the end. The programming command can set any one bit to a 0 bit, and even though the datasheet said that it could only work on 256 bytes at a time, unlike the checksum command, it'll actually just write to anywhere you ask it to. So we can just progressively zero out those bytes. 0 byte, read and save the checksum, do it again, get to the end, guess the last byte, and then work backwards until we figured out the entire block. This feels a little risky because we are actually deleting data out of the chip, so we kind of only get 1 shot at this per lock that we buy anyways. And so we made our tool do the checksum 3 times, and if anything doesn't match, we're streaming all the data to a log and just giving ourselves every opportunity to recover if something isn't quite working perfectly. We programmed in a test pattern into the chip, and we gave this a try, and we found that it worked. We got exactly back out what we had put in, so the concept applies, and at this point we're feeling pretty confident about this and ready to try it on the real lock. So the first thing we do in order to start this process is we issue the chip erase command, because that was part of the testing process to get the test pattern in. That actually also erases the value of the lock, and we get to have the fun joy of spending another $100 on another lock from the same seller and waiting around for a week feeling kind of silly for having done that. It was kind of a bummer, but we kept moving on and eventually got our new lock. This time, we triple checked the code that we had actually commented that part out, and it was not going to run chip erase, and successfully didn't do it. But the attack didn't work. So you wait a week to try it for real, and no dice, because writing was disabled on this chip with the security bits. I would have checked that on the last one, but the chip erase also blows away the security bits. So we're going to need a new plan. We're going to need a different way to get the data out of this chip.
All right, so we go back to our old friend, the app note, for more wisdom to see what else it may hold for us. So we look back at the command list. It's pretty bleak. We already ruled out all the commands, although there was an interesting one. If we think about the programming command, that command does interact with the flash. It does some interesting things that we discovered while erasing our locks. So the way programming works is you send it to command byte, you send it where we want to write, you send it how many bytes we want to write, and then we get back an acknowledgement from the microprocessor. And then we send data bytes one at a time. Every time we send a data byte, we get an acknowledgement. And we get an acknowledgement if the write was successful. So what happens if you were to try programming a microcontroller that, for example, had the write bits locked? What happens in that scenario? So it turns out we actually get an acknowledgement back from the original programming command. We send the first byte here. That one goes okay. And then we get a knack. And it says that we get a knack, do we get a knack because writing is disabled? What's going on here? So if we look at the data sheet, I mentioned it's full of these awesome flowcharts with detailed analysis of what's really going on. This is the branch where we decide to go from an ACK to a NAC, back from our device. And they list a couple of detailed conditions that can cause this to happen. So if we kind of look at these weirdly specific errors, the first one is write data received, but write error. And then there's write data received error, but write error. And then there's my personal favorite, write data received error, but write okay. And so how does this happen? How does this write data received? I know I'm sending the data properly, if it got received properly, but there was a write error. How does this actually occur? And you'll notice something else interesting. There's no such error condition for security bit set. That's not something that they're checking as part of this flowchart. And the thing to keep in mind is that IC designers are incredibly efficient. Every single bit of logic they include takes up space. And in IC design, space is money. Every square millimeter costs money. So there's no more logic than absolutely required to implement the datasheet specifications. Usually there's no 4D thinking going on. There's no hidden information. So how would you implement this command? So we got to think about what's going on under the hood as this runs in the silicon. So this is my hypothesis. We have 3 steps. Step 1, we receive the programming command. We acknowledge it. Step 2, we receive a data byte and write it to memory. And then step 3, we verify that the data byte that got sent to us got written into memory. So if we think about how does this interact when we have those security bits set? What's going on inside the chip? So we could block the programming command, and there's a security bit, but that's probably not what's going on. If you recall, we got an acknowledgement back from our programming command. So that's not what's going on in this case. In step 2, we could block the actual writing of the data. We could have some kind of write disable where we're blocking the data path going to the actual memory, something like that. That could be how this is working. We did get that error that says write data received, but write error. And so in step 3, we verify that it was written. But how does that actually happen? How are we verifying what got written to the memory? So my hypothesis is in step 3 must read the actual byte from memory. It must know what's really in that physical address in order to tell us that something went wrong. So how might we be able to exploit this? So what happens if we program the same data byte back into the same point in memory? What do we get then? So we tried this. Turns out we get an acknowledgement back. So this tells us what value of memory was in there, if only we can guess correctly. So now we're ready to pour out the memory. So the first step, we write 00 to the first address. And then if we get a NAC, then we write the next value, 01, 02, 03, etc. And then when we get a NAC, we got the real value. And this gives us the great way we can decode stuff Hollywood style, 1 byte at a time, decoding it all the way down.
So we were able to get the data out of the chip. And now that means it's time to actually figure out what the program does and disassemble it, decompile it, just understand what's going on in there. The way I would usually approach this is take the code and pull it up in Ghidra. Maybe some of you folks prefer IDA Pro or Binary Ninja or another tool, but what all these tools have in common is they do not have support for this ancient core that probably wasn't that popular. So we looked around for open source tools, other things from the manufacturer, and there just was not any disassembler for this part. There were a couple open source ones for similar parts, but they just actually did not work on the code we fed them. So we're going to have to write our own tools. We're going to have to make our own disassembler for this part. And the process of doing this, fortunately, was a simple instruction set, relatively speaking. We basically start by taking every instruction as it's defined in the datasheet and transforming that into kind of this machine-readable Python class for each instruction that tells us, what it looks like in binary, how it affects the flow of the program, which is important because it's not fixed length instruction words. We can't just decode every location in memory and see what instruction it is. We have to understand where every instruction starts by sequentially decoding them. And so Mark contributed the bulk of the instructions with some incredible combination of Excel, Python, and ChatGPT generated.
Parsing PDFs is awful.
Yeah. But we, ended up with 100 or so of these instruction classes just kind of operated by a driver to check each location, check each, interrupt vector and reset vector and then just branch out from there. And we got the assembly for that, and then we went through the process of kind of manually turning that back into what I thought the C code would have looked like, because that's a lot easier to read, especially when the whole thing is peppered with 16 and 32-bit operations that this chip actually can't do. Those are the most annoying to read in assembly. Anyways, we got through it, and if anybody here ever runs into one of these chips, one of these 78K0S chips in general, or more specifically, this series was a 78K0S KU1+. You can use our tools and get its code out and figure out what it's doing. And if you do find one of these products, if you find a product using one of these chips, we'd love to know about it. We'd love to know how prevalent they are in things that were made recently. We'd also like to thank the Renaissance product security team for being very responsive to the disclosure we sent about this. They pretty understandably took a look at it and said, yeah, this is a 40-year-old discontinued part. It really doesn't matter. But it was nice of them to get back to us on that so quickly. So now we're going to show you a demo. It's going to look like this on the table. I'm putting up the picture because it's kind of small.
While we demo, we will accept questions.
Yes, ask away.
So what happened was the write command was actually disabled, so we weren't able to clear out those bytes in order to roll back that checksum.
Any more questions?
Any hope for undocumented commands?
Maybe. I hope they're kind of, I mean, that'd be cool, right? But we didn't find a way to get, like, I would love to look at the boot ROM, right? I'm not sure there is a boot ROM. It could very well be just hardwired logic. We scanned every possible memory address and didn't find anything that looked like built-in executable code. You will see in a second there is some hidden addresses that aren't documented, but they're not executable. So we made our tool very simple. You just hit enter, and it spews out every address and the value that guessed correctly. We optimized this a little bit by kind of figuring out the statistics of what bytes were most common in this bytecode and guessing those first. But other than that, it's, you know, trying a few ones that are particularly hot and then just going sequentially. There's 4,000 bytes of data for you to ask questions during.
Was the decompilation manual or
the decompilation was manual. Yes, at many points, especially towards the end, was thinking I should have just bit the bullet and implemented this as a Ghidra module, but I didn't. So it's just all manual.
Fueled by Mountain Dew and tears.
Please use the mic for the question so we can record that.
Do you know why your power analysis failed and only got half the data?
It's a good Mark question.
What was the question? I'm sorry.
Do you know why the power analysis failed and why we only were able to get 4 bits of data?
So normally in power analysis, when we only can see switching events. We can only see 1 to 0s or 0 to 1s. So normally we can actually only get 3 bits per byte of information because there's only 3 different combinations of switching between 0 and 1s. In this case, there's a little bit more shape to the pulse, like it takes a little bit more time to propagate, so we get 4 bits per byte, but it actually would have been really uncommon for us to get multiple bits per byte. We were hoping we might be able to get more processing to see the checksum incrementing or more internal states, but we were really only able to see flash readout in the power trace.
Great talk. I think that readout, that 4 bits is pretty interesting. Could you do a timing attack and measure the timing of that?
We did look at the timing. It was actually very, very, very same. It was very repeatable across every byte and every different system. We even looked at, we hope the verify commands, those are usually good timing attack targets, like we can decode it 1 bit at a time based on a fail, but the verify in this chip doesn't actually take any data. So we looked at all those kinds of possibilities to understand what might be there, and unfortunately we didn't find anything.
I see. And do you know which bits you were able to extract, or no?
Yeah, we were able to basically bin every byte into 16 different power traces. So there were a bunch of different bytes for every one of those different shapes.
I see. I'm curious if combining that with a checksum would then allow you to reveal some more data. But I mean, your guys' attack made a lot more sense. Very cool. Thanks.
Thank you.
So you had 2 attacks here, and the first one with killing off the bytes to zeros, as you're able to drop bits but not raise them in the state where reads are locked out but writes are not locked, would have allowed you to dump it, except that it was in a more secure state, so you had to use the second attack. The transition between them, if you get a chip that is locked against reading but not against writing, where your first attack would have worked, are you able to increase the security of that such that this attack would work? Or are you like stuck in the middle and unable to raise it?
That's a great question. Yes, you can disable writing if you want to do the second attack, and that's exactly what this thing does. Is the very first thing it does is actually disable writing, because it's a lot more convenient that way. And then once you learn the value of the chip, we still have access to the chip erase command, so you could knock everything out, including the security bits, and put it back to its original state. Let me see if I can increase
that was actually our biggest fear, is we would, the second one would be different, and we would blow away another $100. Spent quite enough on locks already.
How did you figure out what the checksum algorithm was? Was it just like XORing it against a constant, or was it in the manual, or?
It was in the manual. It's not really exactly a checksum or a CRC. It's kind of some weird custom thing they cooked up. But fortunately,
it's strictly worse than both. It's god awful.
Yeah. But yeah, it is. It's very odd. But they did give a C code for it, so we just used that. I guess I'll point out one interesting thing. I wish I could make the font size bigger, but I can't figure out how to do it right now. This is actually not documented Flash at the end here. There's some just weird data at the end. And so if anybody wants a fun project, you should figure out what that means, because I only found that while making this presentation, and I didn't have a lot of time to look at it. Just weird undocumented data at the end of the memory.
All right. Well, thank you guys. Feel free to chat with us about it. We'd love to talk to you guys.
Yeah. Thanks, everybody.
Thank you very much for the talk.